Precision Measurement for Machinists, a MasterTask multimedia program. Lesson 2, Geometric Dimensioning and Tolerancing. This is an example of a part print which uses geometric dimensioning and tolerancing. These symbols call out different geometric tolerances. Geometric tolerances use geometric forms, such as planes, lines, and cylinders, to control the shape and dimensions of workpieces. Geometric dimensioning and tolerancing, commonly called GD&T, is in widespread use today. This is because of the many benefits it brings to engineers and designers, machine operators, setup personnel, quality inspectors, nearly everyone involved in manufacturing. There will be 6 parts in this training tape. In the first part, you will learn the basic principles and terms of geometry which are required to understand GD&T. In Part 2, you will learn the basic concepts of geometric dimensioning and tolerancing. Part 3 will show you how location tolerances for GD&T are different from and better than older-style coordinate location tolerances. In Part 4, you will learn about material condition modifiers. This understanding is critical to being able to correctly measure geometric tolerances. Part 5 will show you how geometric size tolerances also control the form of workpiece features. And in the 6th part, you will learn how geometric tolerances are called out with a feature control frame. Part 1. Essential Geometry for Machinists. In today's manufacturing industry, an understanding of basic geometry is essential. Reading part prints, especially ones with geometric tolerances, correctly measuring workpieces, even setting up or operating machine tools requires a knowledge of basic geometry. Much of the information in this part of the lesson is theoretical in nature. It deals with abstract ideas and concepts. However, these abstract ideas have a direct correlation to manufacturing and inspection procedures. The most basic building block of geometry is the point. A geometric point is a single location. It has no dimension or size, not length, nor width, nor depth. The point you see here is exaggerated for viewing purposes. It appears to have size, but a true geometric point does not. All other geometric forms are made up of points. The next geometric form is a line. A geometric line consists of a single, perfectly straight row of points. There are an infinite number of points in a geometric line. Remember that a point has no dimensions. A line, however, has one dimension, length. There is no width or depth, but there is length. Although a line is made up of an infinite number of points, only 2 points are required to define a line. Imagine a single point, such as this one. As soon as a second point is selected, anywhere in space, a geometric line is defined. This line consists of the straight row of points which intersects the 2 defining points. The next geometric form is a plane. Remember that a point has no dimensions and a line has only one dimension. A plane has 2 dimensions, length and width. It consists of all the points and lines which exist within a 2-dimensional space. All of these points and lines, for example, lie within this plane. These points are not part of this plane since they are outside the 2 dimensions that make up the plane. These lines are not part of this plane since they extend outside of the plane's 2 dimensions. Some of the lines intersect the plane, but they are not part of it. Just as 2 points are needed to define a line, 3 points are needed to define a plane. By selecting any 3 points out of an infinite number of points available, a plane will be defined. A plane can also be defined by any 2 intersecting lines. In order to make the geometry of planes more understandable, the lines which are selected to define a plane are typically perpendicular to each other. The 2 lines which are chosen to define a plane are labeled with a letter, typically X and Y. The lines which define the plane are more critical than the other lines that lie within the plane. Because of this, we will give these 2 lines a name. We will call each of the lines which define the plane an axis. So we now have an x-axis and a y-axis. Because we have labeled these lines, any point which lies within the plane can be identified. Geometric planes are often identified by the axis lines which define them. This plane, therefore, would be called the xy plane. Let's begin at the point where the two defining lines or axes intersect. This special point we will call the origin, since it is the point from which the lines originate. Let's take a closer look at the origin point. We will number the origin 0. By counting 5 points to the right of the origin, for example, then 7 points up, we reach a point which could be labeled x5, y7. These letter and number pairs which identify the specific point are called coordinates. If we wanted to identify a point on the other sides of the intersecting lines, we would simply count in the opposite direction using negative numbers, -1, -2, -3, and so on. This system of defining points within a plane may look familiar. It is called the Cartesian coordinate system, and you may have learned about it in your early school years. This system may also look familiar if you have ever operated a CNC lathe. This is the same system of lines, points, and coordinates within a two-dimensional plane that is used to control the precise movement of a lathe cutting tool. Suppose that we want to expand our coordinate system to a full three-dimensional system. Now, in order to add a third dimension, all that is needed is a third axis line. This axis line is perpendicular to the first two lines. We will call this axis line the z-axis. This third axis is combined with the first axis, the x-axis, to form a second plane, the xz plane. It is also combined with the y-axis to form the third intersecting plane. This plane is called the yz plane. This coordinate system is now extended into 3 dimensions. The 3 planes make it possible to locate any point out of the infinite number of points which theoretically exist. This three-dimensional coordinate system is the same coordinate system used on CNC machining centers. Since it allows any point in three-dimensional space to be located and defined, this coordinate system permits controlled movement in any direction to any location. Typically, the primary axes on machining centers are labeled or addressed as X, Y, and Z. Coordinates in a three-dimensional grid require 3 values, one for each axis or dimension. Another basic geometric shape is the circle. A geometric circle starts from a given center point. Then, by selecting all of the points which are located in equal distance from the center, a circle is created. A circle, like a plane, is two-dimensional. It has no depth. 3 terms are commonly used when dimensioning or measuring circles. The circumference of a circle is the distance around the outside. The diameter of a circle is the distance measured from one point on the outside edge to the point on the opposite side. Lines used to measure the diameter intersect the center point. The radius of a circle is the distance from the center point to any point on the edge. The radius of any circle is exactly 1/2 the diameter. Now imagine drawing a geometric line through the center point of a circle. This line is perpendicular to the circle. Now we add more circles, all the same size as the original one. The center point of each circle intersects the perpendicular line. We have just constructed another basic geometric shape, the cylinder. The shape of a cylinder is like a tube or a shaft. A cylinder is the same diameter at any point along its length. It is also perfectly straight, since it is created with a perfect geometric line through the center. The line which passes through the center of a cylinder is called the axis of the cylinder. Now, geometry deals with not only shapes, but also the relationship between shapes. For example, imagine 2 straight lines. At any point along their lengths, the distance between the 2 lines is the same. Even if these lines were extended in infinite distance, they would never intersect each other. These 2 lines are said to be parallel. This relationship between geometric shapes, such as lines or planes, is called parallelism. Planes, circles, and other flat shapes can also be parallel if they are equally distant at all points and never intersect. Another type of geometric relationship is perpendicularity. Perpendicular features are oriented 90 degrees from each other, such as these 2 lines. Planes and other flat geometric shapes can also be perpendicular to each other. There are numerous other geometric shapes and relationships, some of which you will learn about during this training program. Part 2. Geometric dimensions and tolerances. Geometric dimensions and tolerances are based on the function of workpieces. For example, this workpiece must simply assemble with a mating part. The alignment of the diameters, called coaxiality, is not critical. Coaxiality is a geometric relationship. If two or more round features are coaxial, a single straight line will pass through their centers. This second piece must also assemble with the mating part. However, since the part will be centered by the threaded diameter, the coaxiality is more critical. This third piece has a very different function. It will be used as a rotating motor shaft. Because it will rotate, the shaft must be dynamically balanced. This requires that each diameter be precisely aligned with the other diameters. The coaxiality is more critical for this workpiece. Although each of these functions have different requirements for the form or shape of the workpieces, these requirements can be easily expressed with geometric tolerances. The machine operator can determine precisely what must be controlled and what tolerances can be used to produce a functional part. There are 5 categories of geometric tolerances. Form tolerances control only the shape of part features. Form tolerances include circularity, cylindricity, flatness, and straightness. Orientation tolerances control the relationship of one feature to another. Orientation tolerances include parallelism, perpendicularity, and angularity. Location tolerances control the location of a workpiece feature. Specific location tolerances are position, concentricity, and symmetry. Because of the tolerance zone created by location tolerances, the form and orientation of the feature are also controlled. Runout tolerances control the form and the location of many types of features. Features which can be controlled with a runout tolerance include cylindrical, spherical, and tapered features and flat surfaces. Profile tolerances control the profile of workpiece features. Profile tolerances include profile of a line and profile of a surface. Geometric tolerances are expressed on part prints by a system of standardized symbols. Each geometric tolerance symbol has a unique, precise meaning. These symbols are sometimes called geometric characteristic symbols. The call-out for a geometric tolerance is shown in a box called the Feature Control Frame. The geometric characteristics, the symbols, and how they are interpreted have been standardized by the organizations ANSI, which stands for the American National Standards Institute, ISO, the International Standards Organization, and the American Society of Mechanical Engineers. Part 3. Geometric Position Tolerances. To control the location of workpiece features in the GD&T system, location tolerances are used. The most commonly used location tolerance is the position tolerance. Position tolerances are measured from the true position of the feature. True position is the exact required location of a plane, axis, or other feature. This is the GD&T symbol for the position tolerance. To understand how geometric position tolerances work, let's first look at a non-geometric position tolerance called a coordinate tolerance. According to this call-out, the center of this hole must fall inside the tolerance zone defined by these 2 tolerances. Since each tolerance consists of an upper limit and a lower limit, the resulting tolerance zone is square. Let's look at how the same tolerance would be called out with GD&T. First, basic dimensions are used to give the true position of the hole. True position of a hole is the exact required location of the axis of the hole. After the true position is established by the basic dimensions, the call-out gives a position tolerance amount. The location of the hole's axis may vary from true position in any direction. Therefore, the resulting tolerance zone is circular rather than square. As you see here, the circular tolerance zone is larger than the square tolerance zone. Under the coordinate tolerancing system, which produced a square zone, parts with holes which fell into the yellow portions of the tolerance zone would be scrapped. They would be out of tolerance even though they would be functionally acceptable. The use of geometric position tolerances eliminates that waste. The position tolerance amount is not the distance that the feature axis may vary from true position. The tolerance amount is actually the diameter of the tolerance zone, 6/100ths in this example. The distance that the hole's axis may vary from true position is 1/2 the diameter, which is 3/100ths for this part. Since no part of the hole's axis may be outside of the tolerance zone, the form and orientation of the feature are also controlled. Any defects, such as bowing or slanting, may not place the axis outside of the tolerance zone. True position is also used to control the position of one diameter in relation to another diameter when both have the same axis of rotation. This type of position control is commonly used with lathe, screw machine, and cold-headed parts. True position of these types of features controls their coaxiality. In this example, the outside diameter is the datum feature. This inside diameter is the feature being controlled. Because the datum feature is a cylinder, the datum is an axis. This datum axis is used to locate the true position of the feature being controlled. The tolerance zone would be cylindrical. It would be centered around the datum axis. The entire axis of the feature being controlled must lie inside this tolerance zone. Features such as slots or tabs can also have position tolerances applied to them. A position tolerance for these features controls the location of the center plane. The perfect ideal location of the center plane is called true position. Like the true position of cylindrical features, the true position of a slot or tab is established by basic dimensions. The tolerance zone for these features would consist of two parallel planes with the true position plane in the center. The position tolerance amount is the width of this tolerance zone. The center plane of the actual feature would have to be located inside this tolerance zone. Part 4. Material Condition Modifiers. Material condition modifiers are used to reflect differences in the intended function of workpieces. Material condition modifiers allow the machine operator to determine whether a part will function in its intended use. He or she can use all the allowed tolerance and still produce a functional workpiece. There are 3 material condition modifiers: maximum material condition, least material condition, and regardless of feature size. A part feature, which is at maximum material condition, sometimes abbreviated as MMC, has the greatest amount of material allowed by the stated size tolerance. We will use a drilled hole to illustrate maximum material condition. These 2 cylinders represent the upper and lower tolerance limits for the size of the hole. When the hole is drilled at the lower tolerance limit, the hole is the smallest allowable size. The smallest allowable hole consists of the greatest amount of material. When an interior feature, such as a hole or slot, is at the smallest size allowed by the size tolerance, it is at maximum material condition. An exterior feature, such as a pin or tab, which is at the largest allowable size, contains the greatest amount of material. Such a feature is at maximum material condition. Maximum material condition is commonly used for dimensioning part features which must assemble with other parts. Maximum material condition represents the worst conditions of assembly. A pin and a hole, which are both at maximum material condition, will assemble, but the fit will be the tightest allowed fit, since it is the material condition with the least amount of clearance. As one or both of the features move away from maximum material condition, the clearance for assembly increases. Maximum material condition is called out in the feature control frame by a capital M in a circle. Least material condition, abbreviated as LMC, is the opposite of maximum material condition. A part feature at least material condition consists of the smallest amount of material allowed by the size tolerance. An outside feature, such as a shaft or tab, is at least material condition when it is at the smallest allowable size. An inside feature at least material condition is at the largest allowable size. An example of the application of least material condition is a tube where a minimum wall thickness must be preserved. In this case, the least material condition of both the ID and the OD are critical. As either of these features moves away from least material condition toward maximum material condition, an increase in the location tolerance may be allowed. It would be allowed because the increase in material would preserve the wall thickness. Least material condition is shown in the feature control frame by a capital L in a circle. The third material condition modifier is regardless of feature size. Regardless of feature size means that only the stated tolerance amount applies, no matter what the actual size of the feature is. Under the current GD&T standards, there is no symbol for regardless of feature size. It is assumed to apply unless maximum or least material condition are called out. On some older or non-standard prints, regardless of feature size is shown in the feature control frame as a capital S in a circle. Part 5. Size tolerances and form control. Under geometric dimensioning and tolerancing, size tolerances apply along the entire length or width of the feature being controlled. Because of this, size tolerances also control the form of part features. The size tolerance of this cylindrical feature, for example, as well as the flat surface, forms a boundary called the boundary of perfect form, or the perfect form boundary. This theoretical boundary is the true or ideal form of the feature. The perfect form boundary is formed by the ideal shape and size of the feature at maximum material condition and at least material condition. The length, width, or depth of the boundary equals the length, width, or depth of the feature. No portion of an actual part feature may extend beyond the boundary of perfect form. On some parts, the boundary of perfect form is not required to meet the needs of the design engineer. When this occurs, there will be a note on the print stating that perfect form at maximum material condition is not required. It is the boundary of perfect form which permits checking of workpieces using functional gauges. The functional gauge simulates the boundary of perfect form. As long as a given workpiece fits or functions properly within the gauge, the part is in tolerance. Functional gauges can only be used when either maximum or least material condition modifiers are applied. Part 6. The feature control frame. Geometric controls and tolerances are expressed by symbols and numbers in a feature control frame. The feature control frame consists of a rectangular box which is divided into several areas or compartments. The first compartment on the left holds the geometric control symbol, sometimes called the characteristic symbol. The control symbol indicates the type of geometric control which is required. To the right of the control symbol is the amount of tolerance which is allowed. If the tolerance zone is circular or cylindrical, the standard symbol for diameter is shown to the left of the tolerance amount. If maximum material condition or least material condition apply to the tolerance, the corresponding symbol will be to the right of the tolerance amount. The remaining compartments identify the datums from which the measurement must be made. There may be 1, 2, or 3 datums, or none at all. There may also be material condition modifiers which apply to the datums. These modifiers will be shown in the same area which holds the datum symbol being modified. In your company, the prints may be drawn up with the datum features to the left of the tolerance amount. This makes no difference in the meaning of the callout. This completes the instruction for Lesson 2, Geometric Dimensioning and Tolerancing. Ask your instructor for the next step in completing this lesson.